Yeah, it started. So the course is called Non-Standard Analysis. Other term which was used in the early years of this subject was infinitesimal analysis, but the scope of this course is of this subject now is much wider. So non-standard is a better name, and you will see further why it is non-standard. Possibly the first historically what I know serious attempt was the work of Leibniz in the end of 17th century about the foundations of infinitesimal calculus, of differential calculus. So Leibniz introduced explicitly infinitesimally small quantities, and for example, frankly speaking, I'm not expert in Leibniz, and possibly no one have the whole scope of his work at hand. For example, because not all of his papers are still published and commented. One of the samples of his work was the following. Consider the function f of x equals x squared. Leibniz wanted to find its derivative. So he argued the following way. Let's introduce a quantity dx which is infinitesimal. Infinitesimal means it is smaller than positive, but smaller than any real positive number. Yeah. Then he writes f of x plus dx minus f of x divided by dx. So what is this? Now he says that let us operate with dx as if it was a convenient number. Yes, just like with real number. So equals x plus dx square minus x square divided by dx. So what is it? It is x square plus 2x dx plus dx square divided by dx, minus x square. So this is cancelled, equals 2x dx plus dx square divided by dx. Now we cancel dx, equals 2x plus dx. And at this point, he says, but dx was infinitesimally small, so it is effectively 0. So here, Leibniz says, but dx is 0 effectively. So this equals 2x. So he killed dx. So in here we see his great inconsistency in his reasoning, because this part, including this, here he operates with dx as if dx were ordinary number, like all other numbers. And here, by some other reason, he says that dx is 0. So this part of this chain of equalities somehow contradicts this part. Yeah? Leibniz, of course, was aware of this shortcoming, and so he tried to avoid it equivocally by saying that in fact these infinitesimals are of different nature, so they are not, I forgot this very complicated scholastic term, so not the words which are meaning something real. No, okay, but nonetheless the mystery remains. So the mystery is here. One moment. The mystery is here. So here is the axis of real numbers. This is 0. These are positive real numbers. And here is some hidden world of infinitesimals. It is here, between 0 and all positive number. So here it is here. And so, in fact, Leibniz was unable to somehow define or in any way study these infinitesimals. Before going further, so I would say that this was done in more or less acceptable form by Abraham Robinson about 300 years after Leibniz. So in between, the analysis was in some sense put on solid ground by Weierstrass, Cantor, Dedekind, and other great people who did without any infinitesimals. They developed the approach based on set theory and limits, starting from Cauchy, of course, what we really studied in our analysis courses. However, this notion of infinitesimals remains somehow, and if you are closer to, say, engineers, they use it more liberally. And even in engineers courses, I would say that I myself also use this term, that I say that dx is infinitesimally small, and the students say accept it without difficulty. So intuitively it is a very attractive subject, a very attractive thing. Of course, if we have infinitesimally small quantities, we should have infinitely large quantities. So we are talking about some extension of the domain of real numbers, because here we have no place for infinitesimals and infinitely large numbers. But it requires a lot of sweaty work. So this will be done in this course. So I mean, I will tell you and you will sweat. But before we are going further, let me start from ordinary, so to say, ordinary numbers, ordinary real numbers. They are ordinary, but nonetheless they are far from trivial. And Leibniz, in his work, he had some intuitive notion of real numbers, but the true definition, theory, and properties of these numbers were found much later, I would say 200 years later after Leibniz. So we'll start from real numbers. So for now we are in real numbers. What I will say, you know in some form this or that form, so I will not get in much details. So real numbers are, the set of real numbers is denoted by R. So what can be said about number? Is a field in algebraic sense. This means that you have two operations. You have operations addition and operation of multiplication with the familiar properties. A plus B equals B plus A plus B plus C equals A plus B plus C. So there exists zero in R such that A plus 0 equals A for any A in R, and for any A in R there exists element minus A in R such that A plus minus A equals 0. It is about addition. About multiplication, similarly, A times B equals B times A times B times C equals A times B times C. There exists element 1 such that 1 times A equals 1 for any A in R. So for any A in R, we have there exists I'm sorry, such that A is different from 0. There exists element, say, A minus 1, such that A times A minus 1 equals 1. Then it is proved that A minus 1 is unique and minus A is unique. So having all this, we have other property, A times B plus C equals AB plus AC. Yeah, and definition. A minus B equals by definition A plus minus B. And another definition, A divided by B equals by definition A times B minus 1 if B is different from 0. Yeah? No such things, I think, are very familiar. From this, we infer the following thing. If you have element 1, there exists element, just a minute, no, it's not here. It is not here. Now, there is another structure here. It is the order structure. So R is a totally ordered field. This means that for any A and B is from R, 1 and only 1 is true. A less than B, A equal B, A more than B. So we have these three possibilities. No, and the usual sign symbol for if A less or equal, and so this means A less or B or A equal B. Now this order is somehow I would say in accordance with the operations, namely that if A less than B, C in R arbitrary, then A plus C less than B plus C. If A less than B, C more than 0, then AC less than BC. So usual operations with order. And other thing which is axiom itself is that 0 less than 1. Okay, so this is a different, I would say, different structure. So we have two structures which are in some interaction. The algebraic structure and the order structure. Now, in particular, let us define. So we have 0, 1, 2 equals, by definition, 1 plus 1. 3 equals, by definition, 2 plus 1. And so on. N plus 1 equals by definition n plus 1. So to the left is the symbol, to the right is the operation. So by induction we define the number n for all n, and we have 0 less than 1, less than 2, and so on. So they are all different. So the set of this n more than 0, let us take positive, is denoted by this term n. And the set n of positive integer number is a subset of R. So we define this important set n, and if you consider the ratios of elements of R, you define the set of rational numbers Q. P over Q, or plus minus P and Q in N. So this is the set of rational numbers. And now two other properties which are independent from what I said before. They, I would say, introduce two other structures. First is Archimedes' axiom. For any real A, positive A, we have two things. A, there exists n, integer n, such that A less than n. And B, also for any in A, there exists M such that A more than 1 divided by M. So 1 divided by n less than A less than n. So it is sandwiched between two numbers, and this is Archimedes' axiom. No, unlike other things which are ascribed to ancient mathematicians, Archimedes really formulated this axiom and used it in his work on measuring areas, volumes, and so on. So it was his working tool, this axiom. So this axiom leaves no place for infinitesimals, because any number, any real number, is more than some number which is not infinitesimally small. So if it is possible, so it is measurably possible. If it's positive, it's measurably positive. Yeah. So this is this axiom, and so what we are going to do, in particular, we are going to create a number system which does not satisfy the Archimedean axiom. So it was called non-Archimedean number system. And the next property, which is of different sort, it can be called, I would say, dedekind completeness. Dedekind completeness. What is this? Suppose A is a subset of R such that there exists alpha such that A less or equal than alpha for all elements of A. So I would say A is bounded. From above. Suppose we have bounded set of real numbers. Then there exists a number let me write it at once, unique number alpha 0 such that A less or equal than alpha 0 for all elements of A. And second, if beta less than alpha 0, less, then there exists a element of our set such that A more than beta. Yes. So this means that alpha 0 is the least upper bound of A. No, alpha 0 can be element of A or it can be not element of A, but anyway such alpha 0 exists. So A can be, if it is bounded from above, it can have no largest element, no maximal element, but the upper bounds have minimal element. Got it? Okay. So this is the property of completeness. We can invent examples of rings, of fields such that they have algebraic properties of field, but no properties of the further structure. There exist algebraic fields which have the order structure. There exist algebraic fields which have the Archimedean axiom but don't have completeness. But and there exist the fields which have all four structures which satisfy all these properties. And the Great Theorem, which I think belongs not to Dedekind, Cantor, maybe some other people. It has different variations and different proofs, is the following. That a field which is totally ordered Archimedean and complete exists. First, there exists an object which has all these properties. Second, such field is unique. Up to isomorphism. What does it mean, unique up to isomorphism? Suppose say F, G are two fields satisfying all conditions. All above. Then there exists one map, say phi from F onto G, some function for any element F, we have some element G, such that F of phi of F plus G equals phi of F plus phi of G. Here F in F, G in G. For all. Phi of F times G equals phi, no, I'm sorry. Phi of F1 plus F2 equals phi of F1 plus phi of F2, where for all F1, F2 in the field F capital, phi F1 times F2 equals phi of F1 times phi of F2. If F1 less than F2, then phi of F1 is less than phi of F2. Yeah? So this is the isomorphism respecting operations and order. So if two fields are isomorphic in this sense, then all the properties of the field which can be expressed in terms of operations and order, they are identical in the first and the second. So only the names of elements change. Yes? The proofs, there are different proofs of this theorem, they all follow one idea. Instead of taking two arbitrary fields and directly establishing their isomorphism, we better take one, I would say, standard field, which we construct somehow by hand, and then prove that any other field which satisfies all four groups of axioms is isomorphic to it. Yes? Now the different proofs use different, say, realizations of this field. For example, in the proof of Dedekind, the field is made of Dedekind cuts. No, I think I will not use them, so I'm going to tell it now. In counters, the elements of this, say, standard field are the equivalence classes of Cauchy sequences. Yeah? I prefer the proof where the elements are just numbers written in decimal systems. So let us write it. Say the numbers, it is written, here is decimal point, here is A0, A1, and so on, AM, and here B1, B2, and so on. This sequence can be infinite. AI and Bj are just the digits they belong to this set 0, 1, and so on up to 9. Yeah? So it is just our ordinary numbers, and here we can write plus or minus, of course, and the operations are just usual operation, usual long addition and long multiplication. Yes? So the difference is that if the number is infinite, then we cannot do it starting from the end. So we have to do it starting from the left and moving to the right. So this entails some maybe complications, but very small. So every concrete digit of the result, say, of the sum, stabilizes after finite number of steps. So it is enough. I read that astronomers have a habit to compute this way, from left to right, unlike all other people. No, now they all use calculators, so the difference disappears. And important is that you have to do some identifications, namely if your number AM A0 dot B1 BN 999 and so on, we identify it with the number am a0 dot b1 bn plus 1. No, if bn is different from 9, so the last digit which is different from 9, and then 0, 0, and so on. So we accept this rule. So our elements are not just the sequences of digits, but sequences of digits with this identification. And then we define constructively, algorithmically, the operations here, and then we prove that first this field satisfies all the 4 groups of axioms, and second that any other field is which satisfies all these axioms is isomorphic to this field. So this is the most constructive proof. I think I read, I think in some paper of Arnold that this definition was used by crazy French teachers when they taught the kids, students in some elementary school. Yes, so I can imagine what is inside the poor heads after this. So if we give this constructive definition and nothing more, then it is formally a model of real numbers, but of course completely incomprehensible. Okay, so what we are going to do, we are going to go past these properties. Yes. I would say that there were different attempts to construct non-Archimedean fields or non-Archimedean extensions of real fields. Especially many of them were in early 20th century. I used to take a mathematical journal of that time, and in one issue I found not less than 3 different articles about construction of non-Archimedean fields. No, one of the most popular that time was the non-Archimedean field. I mean, a field which has the same algebraic property, but and has the total order which satisfies all, but is not Archimedean. Where can we take these elements from? Here I wanted to tell what I will tell, and or maybe I will not, but you will see many times that if you create something which you want to name numbers, then these so to say numbers can be done of completely different material. Yes, that as they are numbers, but in fact they may be, say, very large and complicated sets. Yes, so here the new, so to say, numbers, let me say a few words about them. What is called rational functions. So what is rational function? Rational function R of x is simply a ratio of two polynomials, p of x divided by q of x. So it is a ratio of two polynomials. And so p of x, q of x are polynomials. Of degrees, say m and n, arbitrary degrees. Operations are operations like functions. So if you have R1 plus R2 as a function of x equals R1 of x plus R2 of x. So, and sum of two rational functions is a rational function. We can this sum somehow write in this order, in this form. Yes, and similarly, R1 times R2 of x equal R1 of x times R2 of x. So it is a pointwise multiplication, or it is just algebraic multiplication of rational numbers. So we can forget about this argument x and simply perform formal operations with these polynomials. Now, what about the order? The order is defined in the following sense, that R1 of x less than R2 of x if and only if there exists, say, some positive t such that R1 of x less R2 of x for all x which are more than t. So it is, I would say, eventually this inequality holds eventually. Yes? And remarkable property of rational functions is the following. It is a theory. If R1 of x, R2 of x are rational functions, then one and only one is true. R1 less than R2. Here I don't write x because it is a relation between two functions, not between their values. Or R1 more than R2 in the sense which is written here. 3, R1 is identically equal to R2. So it's one and the same function, up to multiply numerator and denominator by the same number or by the same polynomial. I don't say that it is irreducible. Yeah. So we have only 3 possibilities. So this means that this field, the field of rational functions, is totally ordered. So why it is true? In general, this is not true, because, say, if we have 2 functions, say f1 of x equal cosine x, f2 x equal sine x, then for arbitrary large x, we can have that sine x more than cosine x and cosine more than sine. So these 2 functions are not fit for this definition of their inequality. So they are not comparable. Yeah? So these functions are not comparable, and if you have 2 rational functions, it turns out that they always are comparable. It's a good problem, just you can think about this, why rational functions are so good and other functions are not. Yes. So this means that, and then this, why this this field of rational function, why it is extension of the field of real numbers? Simply because we can, I would say, embed real numbers into this field of rational function. So it is of R into this field is called R of X. The field of rational numbers. We take A, which is in R, and we put in correspondence to A the following function. Ra of x is identically a constant. Constant is also a rational function. So the constants form a subfield, because the sum of product of the constants is a constant. 1 is a function which is identically 1, 0 is a function which is identically 0, and all the properties of real numbers go through to this subfield. So we can say that R is a subfield of R of x. Yeah? So we have a subfield. So it is extension of Rx of R. So it is a wider field which contains R and has the same algebraic properties as R, and it also has an order. Here the order in R is the same as order in R of x. The same. So we extend the set R as a set, we extend it as a field, and extend it as an ordered field. And now, why Rx is not Archimedean field? Not Archimedean. Let us consider the following function. R of x equals, say, 1 over x. And let us take any constant. A 0. A is element of R of x. So it's a function which is identically A. It is this function. Then, for x more than 1 over A, 1 over x less than A. And this means that this function R of x in our sense less than A. Okay? So this function 1 over x eventually becomes less than A. R of x less than A, and A can be arbitrarily small positive number. Yeah? Or arbitrarily small positive constant function. This means that there is no, this means that R of x, I would say, there is no n such that R, let me write, less than 1 over n. This means that I'm not interested in this argument because, again, this relation for the rational functions relates not to the values of this function, but to the functions themselves. It is a new relation. Yes, so in this sense, this R less than, there is no n such that it is more than 1 over n. So it is opposite to Archimedean property. So the say axiom does not hold for R of x. This non-Archimedean field and even more, the following is true. You can somehow figure it out yourself that the field R of x is not Dedekind complete. Yeah. So it is not Archimedean, not Dedekind complete. We can use it in some restricted sense, but we can immediately see that this field is not satisfactory for the purposes of analysis. No, one simple thing. We have here not only infinitesimally small elements, but also infinitely large elements. So the function, say, s of x equals x, for example, satisfies s more than a for any a in R. So this growing function, it becomes eventually larger than any constant, of course. So this means that s this function s equals x is infinitely large, or infinite element. Yeah? So s is infinitely large. So we have this function. We have infinitely large, so to say, number, so elements of this field. But let me ask a question. Do there exist infinitely large integers in this field? We have integers in the field of ordinary real numbers, but what about integers in this field? Yeah? Integers also, what about integers? They can be even and odd. Yeah? Can we find elements of this field which have the properties of even and odd infinite numbers? The answer is no, I would say no. I don't know such things, and I don't know the way how to define these elements. And or what are infinite and prime numbers? Yes? Do there exist infinite prime numbers? At least in this field, nothing like this exists. Yes? Or if you have an infinite number, if you want to define exponent of this number, e to the power infinite number, or infinite element in the field. Again, if you try to define it, you go immediately beyond this field, say e to the power x itself, and this makes your makes this business hopeless. So this is not enough. So this field is a good intermediate point, but it does not satisfy us. It does not give us sufficient, I would say, sufficiently powerful tools to work and get good results. And this was more or less the state before the people from the side of mathematical logic started working about this problem, how to find, how to define this field, which is genuinely good for analysis, which is as good as ordinary real numbers, or even better. And the final stroke was made by Abraham Robinson in early 60s, who really founded this discipline, non-standard analysis. And why non-standard? It will be seen next time. What does it mean? Maybe not next time, but I will start next time. And now I have 9 minutes left, and there is no sense in starting something new, so let us finish now. If you have some questions, please ask me. Yes, please.
Will we be able to define integers in this field by the end of the class?
In this field of rational functions,
Yeah.
I don't know. I have no idea how to do it. This was one of, I would say, the things which were done very, I would say, freely and elegantly in non-standard analysis, which cannot be done in this example. So this is a dead end. Other questions? Yes, please.
If we replace R by any totally ordered field, does all this still hold? Can we define a totally ordered field of rational functions for any totally ordered field that is not necessarily R?
But you don't assume it Archimedean and complete.
Yeah, exactly.
So we have a lot of such fields. I don't know. I don't think so. So we can consider, to make it more material, we can consider, for example, a field is the set of R1 plus R2 times square root of 2, such that R1, R2 are rational numbers. Yeah? So such a field, which is called Q of square root of 2, it is an ordered field. We take the order from real numbers. No, okay, it is Archimedean, but not complete. But how can it help you? Here, we can consider rational functions, say, defined on this field only, with coefficients from this field, with the same definition of order. And what else? I don't see any way how to define infinitely large integers in this field. Again, maybe we can ask some specialist in number theory, but I fear I did not see anything like this. But nonetheless, I'm going to explain different way. Okay, so let us finish, and thank you for your questions.